Okay. So in this part lecture, we'll start by looking at dependent rounding. Then I'm hoping to give a sort of a brief overview of other techniques in especially randomization techniques that have been very effective in solving large and hard optimization problems on graphs by actually looking at simpler graphs. Okay, and I'll have some slides on it, but we'll hopefully cover some interesting problems there as well. Okay, so let's go back to this situation of dependent rounding. So here, this is the goal. We want to give a randomized algorithm to generate 0, 1 random variables such that you have the expected value of xij equals xij, the degree we have this, and we have si subset, this is what I have written, this is the condition, the third condition. Okay, let me just state that again, that is, if you look at all the, for every vertex I, you want any, the variables corresponding to any subset of its adjacent edges subset of its edges should be negatively correlated. Any subset of its adjacent edges should be negatively correlated. Okay, so a priori we really don't know how to deal with this, and in fact it's not even clear how to do A and B together, but we will see a nice scheme to achieve this. Okay. Okay. Very good. Okay, so at the outset, I had started defining this bipartite graph, and what we will be working with is the bipartite graph, but you don't have to worry about it. We will see at what point the bipartite assumption will actually come in. Okay, so is the setup clear again? What we want to do is we have this bunch of numbers associated on each edge, which is the number between 0 and 1. We want to have a way to define a random variable that has its expectation equal to that number, but the degree of every vertex you want it to be, in any random choice, you want it to be either the ceiling or the floor of the degree in the summation of the xij's. Summation xij and capital Di. Okay, so how do we go about doing this? As I said, the first thing would be just picking each ij edge with probability xij. That achieves A, but it doesn't achieve B, so what do I go? So what we will do is we will actually do an iterative procedure. Okay. And what we will, so initially we will maintain this variable called yij. Okay. And initially this variable is the same as xij. Okay? This is the variable that we'll keep changing. At the end, this variable will have a value, and we will define xij equals yij, because at the end this yij will be a 0, 1 number. Okay, so we are always going to work with these yij values. These yij start off being little xij, and we'll keep updating them, and at the end they will all take 0 or 1 value, and that's what we will call them as xij. So some things we will always guarantee is we will try to maintain some invariance. One invariant we will maintain is that the expectation of yij is always xij. Maybe I should use a capital. That's fine. 2, we will maintain the following. These yij's, let's call a yij. If yij is 1, then we'll call it as rounded, 1 or 0. Otherwise, we will call it as floating. Once rounded, remains rounded. So let's think again. So we have a graph. Okay, there are some values on this: 0.2, 0.1, 0.3, 0.8, and so on. These are all the x values. We will initially set these to be y values. As time goes along, some of these values will change. Okay, 0.2 might become 0.5, 0.1, and so on. And at the end, all of these have to become either 0 or 1. But during the process, as they change, at some point, one of these, let's pick an edge. The number on that edge might become either 0 or 1. Once it becomes either 0 or 1, it will stay at 0 or 1. We will never change it. Okay? That's the property of this process. Okay, so now, how do we go about, so this seems, as I said, easy because we can just do it separately for each xij. How do we try to maintain di? Okay, this constraint. How do we try to make sure that, so just to give an example, let's suppose we had this vertex. It has only 2 edges. This is 0.5, this is 0.5. Okay? What do you think we can do with these 2 edges?
So we first pick the first edge with probability 0.5.
Okay?
So if it gets picked, we reduce the probability of the second edge.
Good. Very good. So if so we pick the first edge with probability 0.5. If that gets picked, then you should not pick the second one. Absolutely not, right? You cannot pick the second one because the sum of those 2 edges has to be exactly 1. On the other hand, if you miss the first one, then you absolutely have to pick the second one. So this is like a constraint. So one suggestion is, if you pick one of them, then you try to pick this one. You toss a coin for this one. If it comes heads, then you take it, in which case you reduce this to 0. If it comes tails, then you don't take it, in which case you increase this to 1. Good. Now if the problem, of course, is now, let's suppose we had 4 of them. This is a bipartite graph, so let's say then you can say I could still try to do something like that. I could pick this. If it comes heads, what do? I take it. I have to reduce each of them to 0. Let's say it comes tails, so I don't take it. What do I do to these? How much do you increase it by?
By the same amount, by take the ratio.
You could say by the proportions you could increase it. That seems beautiful. So now we have an algorithm, but now you notice there are some issues. There are some edges here also, right? And this has something going here and so on. If you, without looking at what's going on for this vertex, if you increase it by some arbitrary point, that affects that vertex. You have to maintain the degree value for that vertex also. Okay? Good. So that's, but there is some sort of ideas developing here. If I pick this, then I can at least, in the 2 case we saw, okay, what we could do. In this case, now we don't know how to distribute it. So iterative procedure, what we're going to try to do is something very, very, really elegant. And by the way, this result, what I'm going to describe is due to Aravind Srinivasan and then a subsequent paper by Gandhi, Kuller, Parthasarathi and Srinivasan. And they have a very nice paper on it which explains things very nicely. So I'll describe to you a procedure which builds up on what we have discussed just now. So let me, yeah.
So these degree constraints are also there for the right hand side as well as
For every vertex, yes. Yeah, these degree constraints.
Only for the left hand side will this idea work?
If you only have it for the left hand side, will that idea work? I think it could work. Yeah. Yeah. Okay, I'm going to erase this. I'm going to assume that we know what's going on here. Okay, so let's consider another simple 0.3, 0.7, and then let's see, this is 0.3, this is 0.7. Let's suppose we had a situation like this, let's say 0.3, 0.7, 0.3, 0.7, 0.3, 0.7. Okay, so here I've drawn a cycle, 0.3, 0.7, 0.3, 0.7, 0.3, and then 0.7. In this case, what could you do? You could pick, with 0.3 probability, you could pick this edge. Once you pick this edge, then this zeroes out, right? And this also zeroes out, but then you pick this 0.3. Then, so with probability 0.3, you pick these edges. With probability 0.7, you pick the other set of edges. And this will maintain everything we have written. Forget this for now, correlated, negatively correlated, but it actually maintains everything that we have written there. You see that? So what did we do? We found the cycle, and in the cycle, what did we do with the cycle?
you fix one edge and that fixed all the edges.
That fixed all the edges. Alternatively, you could see we actually picked matchings. There are 2 matchings. So you took the cycle that split into 2 matchings. We either picked one matching or the other matching. Okay? But of course, that seems too simplistic, but essentially we're going to do that in a more general setting. So here is the procedure. And our procedure is just going to repeat the same thing again. So find a cycle or a maximal path in Okay? So what we will do is we will find a cycle or a maximal path in G. So let me assume it's a cycle for now. Okay? Now, in the past example, the previous example, I said 0.3, 0.7, so that was all beautiful, it all worked out, but really we have no control on how these numbers look like. It might be 0.2, 0.3, 0.1, 0.6, 0.2, 0.3. Okay? Why could it look like this? Because there are lots of other edges which I have not drawn in this picture. Okay, so if we have this situation, what will you try to do in this case? Okay, the problem is, since there are other edges that are not there that I have not drawn, there are other edges that I have not drawn, it's a little bit risky to just with 0.2 probability decide to pick this or not, and if it doesn't get selected, throw all that weight into here. I cannot do that, right? I'll have to distribute it somehow evenly, so I cannot do that. But what I want to do is, with these numbers, I want to switch to I don't want to go from these numbers directly to ones or zeros for everybody. I want to go in a smooth manner. So looking at this picture, I can I see you do see a matching, right? There is, I have two colors here. There are two matchings. One. The other matching is okay? Good. So we have two matchings. So now to this matching, 0.2, 0.2, 0.1, 0.2. So this idea that we did with 0.3 and 0.7 was, we either moved all the 0.3s to 0 and the 0.7s to 1, or moved all the 0.3s to 1 and the 0.7s to 0. Let's try to do something like that here. Of course, we can't do the same thing. I can't move the 0.2, 0.1 and 0.2 to 0, all of them simultaneously. But I can do the following. I can decrease 0.1 from each one of them. You see that? So what I can do is, I have the following options. The green, I decrease by 0.1. If I do decrease them by 0.1, where should I put those 0.1s? On the pink edges, right? So the pink one goes up by 0.1. This is great. What's the nice thing about decreasing by 0.1? What's the nice thing about decreasing the green ones by 0.1? One of the edges has now become a 0, so we are making progress. Eventually we have to put all the edges either 0 or 1. Well, this is not the only thing we can do. We could increase this by some amount and decrease this by some amount. What is the amount that I can increase this or decrease this so that I make progress? 0.3. I can make this 0. The other option is I could have increased this by 0.4, but I cannot really decrease these by 0.4. I don't have that much. So, so the only other choice is I increase this by, what did we see? 0.3, right? Decrease by 0.3. Right? This is really like shaping up to be a nice way to think about it, because now you make sure that you're guaranteed that the values that you have changed satisfy that the sum of the values around each vertex remains exactly the same as it was before. Right? The sum of the values are exactly the same as that we had before. Okay. Good. Now, I have these two options. Which of these options should I choose? And if I choose it, with what probability should I choose? Okay. So here I want to make sure that my expectation always remains the same, right? So the probability that, so right now the probability with which I want to pick this edge, it should be 0.2, okay? The probability with which I want to pick this edge should be 0.2. Now, these I'm decreasing decreasing by 0.1, and I'm increasing the others by 0.1. Here I'm increasing by 0.3, and I'm decreasing this is 0.3. So I want to find out alpha and beta such that, let me erase this. So I'll find alpha and beta. Let's call this alpha. This is alpha, this is beta. Okay. So with probability P alpha, I want to do A. With probability 1 minus P alpha, which is P beta, I want to do, let me just call it P actually. With probability P, I want to do A. With probability 1 minus P, I want to do B. Okay. But the expected change, what should be the expected change for each edge? I want it to be 0 because I want the eventual expectation to be exactly the same as before. So I don't want the expected change to be 0. So how do I get the expected change to be 0? Well, I want P times alpha plus 1 minus P times beta equal to 0. So what do you think P will be equal to? Beta over alpha plus beta. Okay. So what is alpha and beta? I didn't write down the definition, but you can. Alpha is the smallest number by which I can change all the greens so that I can add to the greens, decrease the greens and increase the pinks so that one of the elements becomes either a 0 or a 1. Pink, so beta is the smallest value that will make sure that when I decrease the, I should say now the small, yeah, okay. The value that will make sure that when I decrease the pinks by that value and the greens increase the greens by that value, then again one of them becomes, one of the edges becomes 0 or 1. So the probability with which I'll do P is beta over alpha over beta, and 1 minus P equals alpha. And it's very easy. So my statement is find a cycle for a maximal or a maximal path in G. Okay, I haven't yet discussed the maximal path case. We'll do that right now. But define alpha and beta, or compute alpha and beta. Okay, alpha is let me write it differently. Cycle or a maximal path P. Split P into two matchings. M1 and M2. Define alpha and beta. Okay. I will write down actually just to be define, I'll give the definition of alpha and beta momentarily. Then with probability beta over alpha or beta, we will do something. With probability alpha over beta, we will do something. Okay, so let me just write down what alpha and beta are. Formally. So alpha is going to be the minimum of two quantities, gamma such that so I'll calculate the minimum gamma such that so M1 is M2 is matching 2. So there are two matchings, M1 and M2. I look at every edge in M1, every edge in M2. I look at the smallest gamma such that Yij plus gamma. Let me make more space here. Okay, minimum. So I'm looking at M1. Okay, so I find either the smallest. So this is I find the smallest number such that if I decrease all the edges in M1, increase all the edges in M2 by that amount, one of the numbers becomes either 0 or 1. This is the opposite. Either I decrease all the edges in M2 and decrease all the edges in M2 and increase all the edges in. So with probability beta over alpha plus beta, I will so there decrease edges in M1 by alpha and increase edges in M2 by beta. So this is what I do here. With this I do just the opposite. Okay, so I just tried to be formal, but I think you can recover it based on what we have covered. So the rounding scheme entirely is this. That's all you do. In each iteration, you find a cycle or a maximal path, and you repeat this. Okay, cycle or a maximal path, and you split P into two matchings. Alpha beta defined with probability this, and either you increase values on one matching and decrease in the other, or you decrease value on one matching and increase on the other. Okay? Okay, so now what two issues. One is what happens when we have a path as opposed to a cycle. So when we have a path as opposed to a cycle, we run into the following situation. We have these two things So let's suppose you have a path. Okay? Okay, so we try to find a cycle or a maximal path in G, split P into two matchings and so on. When we try to find this, notice that we are only going to be working with, if an edge was already converted to 0 or 1, we really you don't want to be working with that at all. So when I say find a cycle or a maximal path P in G, I'm only talking about the G consisting of the floating edges. The edges that are already rounded, I can safely set aside. I don't have to worry about those edges. It is 0 or 1. Okay, so now when you find a maximal path like this, so in the maximal, when you have a cycle, then what is the nice thing about this cycle? For a vertex, one edge has increased, the other edge has decreased by exactly the same amount. So its degree remains the same. In the path case, the statement is true for this, for this, for this, and for this. But for these two, it is not true. Right? But the nice thing is, the fact that this is a maximal path, what does it mean? What does it mean that this is a maximal path? Already been rounded. So for this vertex, all the other edges have already been rounded. For this vertex, already other edges have been rounded. So this is the only node, only edge for which it had a value of, let's say, 0.3. Eventually, this is going to become either 1 or 0. And that is where, because you're now violating that constraint, right? Its degree is no longer going to match the exact degree of the original value, but it's never going to go beyond either the rounded up or rounded down. Because this particular number will either go to 1 or 0, which will mean that it will never be off by more than 1. Okay? Yes?
So you assume that you have first taken care of all the cycles?
Not necessarily. This is maximal. It's a maximal path, meaning it's possible that there might be cycles some other portion of the graph. But here, this is a maximal path. That's all we are saying. There might be cycles.
Increase the length of the path. So from that 0.3 edge,
Yeah.
you can have an edge going inside in the same vertex, a cycle inside there. So from there to the second vertex. The second vertex. Something of that.
Okay. So, okay, good. Yeah, no. So this is not, so then I won't call this a maximal path. Then, let's say this was 0.2, right? Because we're talking about floating edges. So then this is not a maximal path because you can always go back this way. Okay? But I think you're getting a question. So what does it mean to say finding a cycle or a maximal path? And how do we find it? That's also a question. So what we will do is, okay, let me pose the question to you. How do I go about finding a cycle or a maximal path in a graph? How would you go about finding a cycle or a maximal path in a graph? Good. You start anywhere and you keep moving. Good. So you keep going. Like in your example, you keep going, let's say from here, and you go here, and you come back. Now you have found a cycle. So if you have found a cycle, then you're going to ignore these two, and then you will just take this as your cycle. No. I want to say that's not necessary. Let me give you an example. Let me give you an example. It's possible that we go like this, we go like this, we go like this, we go like this, and we find another one that's like this. So then I can choose this path. But I've not taken care of all cycles. Because I just found this path and this is a maximal path, so I can choose that. Okay, so let's look at this algorithm. I start from any vertex. I keep going and until I cannot, either I cannot proceed any further. Will that be a maximal path? May not be at the other side. So you have to go to the other side also. There are lots of ways to fix it. You can go on the other side, also do the same thing. Okay, good. So, but that's basically that's the whole procedure. You can see this is linear time, just doing depth first search. You can do this in depth first search linear time. You split P into two matchings. This is easy. You do alpha, beta, define this. This is easy. You do this, and you repeat. In every step, you're eliminating at least one edge, making one edge rounded. So the whole procedure takes time, the number of edges times the number of nodes, times the number of edges squared, actually, because you can actually do this a little faster, the cycle or maximal path, but no more than number of edges squared. Where did we use that the graph is bipartite? Exactly. So if this was an odd cycle, then I can still get two matchings in the odd in the odd cycle, but they won't be and you will run into issues, right? So let's say, actually they won't cover all the edges. So if I have a triangle, then I can get this matching and I can get this matching, but then it won't cover this. So I cannot possibly increase two of them and decrease one of them. So this idea doesn't work in a non-bipartite graph. All right. So however you want, you can add any weights on the edges that you want. Okay. You can assume that the graph here doesn't even have weights, and we can give a hint on what graph this is, but you could think about it. There is the claim is that really you cannot have a tree spanner. That's the point about this. The tree spanners do not exist. It's impossible, because once you're fundamentally a tree breaking cycles, right? So just think about it. If you look at this graph and suddenly you're trying to break a cycle, what are you doing? The edge that you're removing, there were two vertices that were very close, and in the tree they could be very far. Okay? So this is the problem for you to think about, and I don't know whether I want to call this as as a problem for your exercise session, but we can decide that at the end. Assume it's unweighted. This statement holds even for unweighted. But this seems like this is like a negative statement, because why are we even thinking about trees when in fact you can't do anything? Okay, because the omega n is terrible, right? That I'm basically saying that you cannot, with tree, you cannot even approximate distances even to within an n factor. It's just hopeless. Then why are we interested in trees?
Maybe you can add some small number of edges to the tree and
Good. That's what the spanner is. But I'm insisting, because notice the spanner is sort of linear number of edges. So you take the tree and it's something like that. It's not quite like that. So it really depends upon what do you mean by small number. But I'm going to relax in the other direction. I'm going to insist that this is a tree. And why do I insist this is a tree? Because for many problems you can actually solve very nicely on trees. There are how you would solve it, right? You would solve it on this subtree, this subtree, this subtree, put them together in some way. Dynamic programming, greedy, you can do lots of different things. So therefore I really, really insist that you have to assume it's a tree. Once you have to assume it's a tree, you cannot do this. Right? So what do? Well, I'm going to relax. I'm not going to insist that you don't approximate every edge. But then it's sort of hokey that I approximate some edges, I don't, so that's a problem. So instead of that, what we're going to do is give me a distribution, a probability distribution over trees. Okay? And what I would like you to do is make your max UV the ratio of the expected dist T UV over make this to be small. Okay, where this expectation is over the t's drawn according to the distribution. Okay, let me state this again. Okay, let me actually write what can be done there and then. So it's 1 o'clock. Do I have 10 more minutes? I can go there. Okay, so here is what can be shown. Approximating graphs or metrics by trees. This is the result. For any g, there exists a probability distribution d over trees over the vertices of E such that, and this is weighted graph, doesn't matter, such that the maximum over all pairs UV of the expected distance in T UV divided by is order okay. And by the way, we have the same condition as before, that the distribution that we have over the trees, every tree in that distribution satisfies this. Okay? And again, where is the distribution coming in? The distribution is coming in the expectation. Okay? So here is the meaning for this. I can give you a distribution over trees. This is a probability distribution over trees. So if you, with that distribution, you pick a tree and you look in that tree, the distance between u and v, that distance will be not more than order log n times the distance in G in expectation. Okay. Now this is there is a big history of this. This was originally a weaker version of the statement was originally discovered by Berthal, and then I don't know when this was, I forget, 3 years. Fakcher and Paul, Rao and Talwar in 2003 got this result. There have been subsequent results where, in fact, this is even possible with these T's being spanning trees of G, where the best factor is not log n, it is log n times some other small factor, but let's not worry about it. But I want to really emphasize the value of a result like this. The value of a result like this is really for many problems. You can, and I can give you a sort of rough sense of what these problems look like. You can, instead of solving it on a general graph, you say, I'm going to just solve it on a trees. Okay? And I'm going to take that solution and send it over to the general graph. But which tree will I solve it on? I don't know, right? Well, I will just draw a tree from this distribution for that graph and solve it. So that is a randomized algorithm, but it will do what you want. You can actually also de-randomize it, but we haven't covered any of that. But you can make it deterministic at an expense, as a little bit of expense. So let me give you maybe one example. But is the statement clear? Any questions? Anybody wants to clarify anything about this? Okay, so so in what situations is this useful? It's useful in those situations where your objective function is some linear combination of distances. Okay. So whenever you have you're trying to compute some kind of network or a subgraph of a graph, or maybe determining certain facilities, and you're trying to minimize some combination of distances, then the point is, since the distances in the tree roughly captures the distances in the graph, you can solve it on the tree. And if your objective function is a linear combination, then it's just a linear combination, and since linearity of expectation comes in, the distances, linear combination of the distances in the tree are a good approximation to the linear combination of distances in the graph. So whatever you do with trees, actually you get a good approximation for that. Okay? So let me give you one example, and this also could be viewed as a problem. In fact, yeah, I think it's a reasonable problem. Let's suppose I give you a graph, and yeah, okay. So I give you a graph G. It's kind of like this multi-commodity flow problem that we described. I give you a graph G, and I give you a particular single source S, then I have clients located at various nodes. Okay. I have K commodities. Okay. And client I has demand Dij for commodity J. Okay. Find a single path for each client to source such that I'll just write down the objective function. The following is minimized. I add over all the edges in the graph. I add over all commodities. This is commodities are K commodities, right? 1 less than equal to J less than equal to K. as to what is the maximum demand that flows to that. Okay. Maximum of D. Okay. Okay, so what we are doing is adding over all the edges of what is the maximum for each commodity, what is the maximum demand that is going through, because all the demand for that commodity can be sort of consolidated, because let's say, let's fix an edge. I just wanted to clarify one thing. Let's pick an edge here, and these are multiple sources, multiple clients. They have paths going through this edge. Okay, and for commodity, let's say for commodity 1, there was demand of 3, demand of 2, and demand of 5. But these are all the same commodity, so think of this like a multicast of or streaming of some video or something like that, so they can all share it. So you pay 5 for this edge for that commodity. So you add it over all commodities, you add it over all edges, that's minimized. Okay, you can see that. So the problem is to show how to get an order log n approximation to this problem by reducing it in trees. And for tree, the problem is almost trivial. You just think about it. It's very trivial. So how you can get, and this, in fact, this is the best approximation known for this problem. Okay, I think can we put the, so I'll just wrap up. I think I'll stop here and then we'll do write down the problem. Thing you can do is cut based, and here again there are two sets of results. One is just using trees, one is using sparse graphs. So for trees, Raki has shown some really beautiful sets of results here. Strongly recommend reading about it, and there is a very nice connection between that result and the result that we have written down there. And there are lots of applications to this. Finally, you can look at we wrote down, there are 4 possibilities, right? You can do distance or cut paste, and within cut paste you can either stick to trees, or you can decide I actually want to approximate every cut but demand a sparse graph. And it's amazing, meaning the cut problem, there are an exponential number of cuts, right? What is a cut? A cut is just a set of vertices. And how many different cuts are there in a graph? I know it's pretty late in the day, but 2 to the n cuts. Can you believe that you can actually construct sparse graphs such that every single one of those 2 to the n cuts is approximated in this sparse graph as well? Okay, and there exists some really very nice collection of results which shows that for every single cut, the capacity in H is within 1 plus minus epsilon factor of the capacity in G, and the number of edges is just linear. Okay, even if the original graph is very dense, you can actually do it very linearly. And there are some nice results here. I think I'll skip all of this. The applications to sparsifiers, they give you improved algorithms for many flow and cut problems. And the nice thing to learn about these is that the fundamental algorithm is very simple. You just have to pick each edge of the graph with a certain probability. That's the sparsifier. Of course, it's too easy to be said because what probability do you pick with is the biggest challenge. And there are several ways to define this probability. But that's it. That's the algorithm. Pick each edge with a certain probability. They work out to be very good sparsifiers, assuming you pick the right probability for each edge. Okay, I think I'll stop here. What I wanted to cover, but I didn't cover, was this very nice result on the distribution of number of cuts of a particular size, which gives you some idea about it, but we'll stop here. Okay, and I think, can we have the board? And so we'll stop with just writing down the problems. tree spanner lower bound. Okay. Problem 2, let me just call this as multi-commodity routing problem. Okay. Okay. The third, this is a demonstration of Chernoff bounds. Okay. Suppose, maybe let me write it down here. Actually, I erased it. But so suppose n balls are thrown independently and uniformly at random. Into n bins. Okay? Prove that with probability at least 1 minus 1 over n, the maximum number of balls in any bin is order log n by log n. Okay, so this order here, there is a constant hidden and you can adjust your constant. In fact, by adjusting the constant, you can make this probability even smaller. Is the question clear? So you have n balls, n bins. Each ball is thrown uniformly at random into each one of the bins. So with probability 1 over n, it goes to bin 1. With probability 1 over n, it goes to bin 2, and so on. Now you want to look at the most loaded bin. You want to look at how many balls there are going to be. Okay, so as the first cut, what is the expected number of balls in any bin? 1. Okay, and that's easy. But this is a deviation question, meaning how far. But you know for sure that there is some bins will have at least 2 balls and so on. So how large can it be? And it says that it cannot be more than order log n over log n with high probability. And in case you feel that that's a strange number to put there, I encourage you to try to show a lower bound as well. Okay, and that's harder, but you can actually show that there exists a bin which has close to that many balls. So in fact, you can show that there exists a bin that has omega log n over log n bins. But that's harder, but that's a thing. Okay, that's third problem. Okay, so now I will erase this. And the fourth problem is improved bound for set cover. So we saw an approximation ratio. Basically, we show that randomized rounding achieves an order ln n approximation Okay. Show that a more careful algorithm and more careful analysis careful approach yields a is that right? Ln n over approximation. Yeah, so basically, so one thing is the hint, look at the rounding step, okay? The particular rounding step, if you remember what we did, we picked each set with a certain probability, and then we just repeated the same rounding step again and again. Do the rounding step more carefully, and you can get this kind of an approximation. Okay. Did you want to give the dependent rounding, or is too much? Okay.
So today for the problem session, we have to go to a room further down this hall. 1, 2, 3, 1, 2, 3. Because there is a movie here at 3 o'clock. So if you come here at 4 o'clock, you'll find other problems.
Yeah.
After this announcement, I don't know whether anybody will
We'll come to the problem session.
the old flop on.
So unfortunately, I won't be able to make it to the problem session, but I will be back here. I'll be seeing more of you on 30th and 31st, and I'll be also here on the 29th. Okay. So I'll see you.